Okay, I think we'll start. So it's a pleasure to have Dr. Nathan Williams, who is currently engineering at our university in Helsinki, Finland. So Nathan did his bachelor's from Anna University uh, here, and then he did his master's from Brunel University, UK, and then his PhD at Reading University, UK. Then he did postdocs at Cambridge and then at Helsinki University, Finland, following which he has been with the Aalto University for a long time. So Nitin's interests are in and signal processing methods to analyze models from this data. So without further ado, Nitin.
Thanks, Sita bro. So thank you for the introduction. Yes, as Sita bro mentioned, I'm based in Aalto University, and like Sita bro said, so my work is on neuroinformatics methods to analyze human neuroscience data, and on building biologically realistic models of data. Yeah, so.
I think your mic is the mic on?
Okay. Yeah, and so I'll be talking about recent work on which encompasses both these topics today. And since it's a fairly small group, we can of course make it interactive. In the sense, I'll go slowly, and do feel free to ask me any questions as we go along. I don't have that many slides, so I think there would be time to answer questions and make it interactive. So in terms of the outline of the talk, I'll just give a brief background about this area, and also a brief overview of my previous work. And then talk about a little bit about felt that the previous work on neuroinformatics method, when applied in isolation, somehow was driven methods unsatisfactory, and we needed brain computational models or biologically realistic models, large scale mechanisms or systems level mechanisms. And in the final part of the talk, I have a few slides on proposed future work on how I would advance this area of work on building brain computational models, and how that would prospectively complement and enhance existing work by IMSC's computational biology group. So just to begin, so of course this is something that we've all wondered many times, I think. How does the brain work? Or to give a specific example, how does the brain enable the complex cognition required in, for example, a chess game? Between this chess game between Magnus Carlsen and Pragnananda. So there's lots of complex cognition happening, as you can imagine. So there would of course be attention to the chess pieces, then there would be perception or vision of the pieces, there would be memory recall of previous instances, there would be a lot of executive function, planning, decision making about the next move, then there would be the actual movement, and then there would be a social cognition element, because there are two people playing this game, and then there might also be some language element about remembering the names of the chess pieces and things like that. So if you could think or hypothesize what might be going on in the brains of these players while all this complex cognition is happening, so what do you think you might see? So I mean, there would be lots of things going on in the brain, but do you have any guesses about what you might observe if you could actually look into the brains of the players while they were performing this complex cognition required, for example, a chess game? So people would give you different answers, but definitely these brain functional networks would be part of the answer, in the sense that people have known for a long time that when people are performing cognitive tasks, there are sets of brain regions which are interacting with each other, and these interactions are reflected by the correlations in the activities of these brain regions. So these would be definitely a part of the answer to what is happening. So in the kind of complex cognition, there may be many such networks interacting with each other, but definitely the brain functional networks would be a key part of this answer. And we also know that when there are brain disorders, like for example Alzheimer's disease.
So these bridges and the vertices, what are they? Like the vertices are neurons, single neurons that you're talking about?
No, so the nodes would be, so what we would call as brain regions, which are large populations of neurons, which are somehow demarcated in terms of the cyto architecture, or like different criteria. So, for example, like there are different criteria to define a brain region. So, the anatomical criteria based on site architecture, for example, but there are also functional criteria just dependent on which spatially contiguous populations which are highly correlated activity. Spatially contiguous regions with highly correlated activity can also be a functional criteria to define a brain region, or there would be anatomical criteria based on the site architecture and things like that.
So essentially, I can draw multiple such networks based on what I am looking at, like whether I'm looking at anatomical categorization or functional categorization.
Yeah. So, for example, if you take the cortex, so there are different brain atlases or brain parcellations, and each of them uses particular criteria, set of criteria to demarcate a region. So, then the number of regions, so they would basically subdivide the brain, subdivide the cortex, and depending on the atlas, you might get anywhere between 50 and 500 brain regions. So, like the most standard is the Broadman atlas, which has 50 regions, for example, just based on cytoarchitecture, but there are also like much more advanced. And then the edges in this case are just reflecting correlated activities. So each region would have some dynamics from that, and then, for example, you can use just for example just partial correlation or correlation, or like some other slightly more complex measure like mutual information to identify the functional connections. In this case, it's directed connections. So you could use something like transfer entropy or something like that to infer the direction of the connections. So that is the functional connections, and then of course I should also mention that each there are these brain regions, and then there are also anatomical connections connecting these brain regions. Not all brain regions to each other, but there is a certain map of anatomical connections connecting the set of brain regions to each other. Disrupted networks underlie brain disorders in the sense, for example, in a disease like Alzheimer's disease or like some other disorder, you would see networks which differ from the healthy control networks, and these disruptions of the networks are considered to underlie the cognitive impairment observed in these brain disorders. So, these brain networks are important, and the disruptions are also important in terms of impairing cognition. So this is what is considered to be the case.
But then disruptions only happen at the edges, or also can happen at the vertices. So we have drawn, it seems like the edges are disrupted.
Yeah, it can also happen at the vertices. It can, for example, lesions, for example. So that would be at the vertices. So I suppose like the current paradigm of cognitive neuroscience is mostly to focus on the network and the edges. So I guess that's why I have focused on the edges here. But for example, even if you think of just a simple lesion, that would be that a certain node is completely out of the network. So this would be a node based. Okay, so and then in terms of studying these large scale brain networks in humans, so these are the three main technologies: EEG, MEG, and fMRI. So EEG and MEG have the advantage of high temporal resolution, and they directly measure the brain activity, but they have low spatial resolution, while fMRI has a high spatial resolution, but it only indirectly measures the brain activity, and it has low temporal resolution. So in my work, I have been attracted by the ability of EEG, MEG to reveal rapid changes of brain activity at the millisecond time scales relevant to cognition. Okay, so then most of my first author and methodological work has been on developing methods to more effectively characterize brain networks observed in EEG and MEG. So this is just a brief overview of the methodological work, both first author and also some middle author papers. So just to give you a brief overview, so this is on the left, so that is work on applying a Markov model based method to analyze time varying networks in EEG task data. So we used this method, and we were able to show that we can discriminate between the EEG activity from two different experimental conditions just based on the Markov model parameters. And then so this is work on applying a multivariate autoregressive model based approach to characterize directed functional networks from MEG data, and we applied that method in collaboration with a clinical neuroscientist, Professor James Rowe, to identify spectrospatial network based biomarkers differentiating different types of dementia, and this was published in this brain journal. And then I have also proposed methods to identify modules, strongly connected nodes, modules in noisy or incomplete brain networks, and we applied the proposed method to identify modules in incomplete connectomes of phase synchronization, which we estimated from intracranial EEG data, and we were able to use that method to identify a set of electrophysiological modules which were different from the traditionally identified module from other technologies like fMRI. And we were also able to demonstrate evidence in favor of these modules representing functionally specialized subsystems which are responsible for specific cognitive functions. And then recently with Professor Arijit Samal from IMSC, so Arijit and I proposed network based measures of higher order network structure to characterize fMRI based networks, and we were able to show that these measures can discriminate between the fMRI based networks of healthy individuals and individuals with autism. So that is this paper, and then in this paper we were able to show that these measures of higher order network structure are sensitive to age related changes in the fMRI based networks. So this is all methodological work, both first author and also like middle author work that I have done. But while doing this, there was always this sense that somehow we are not getting at the crux of the problem, or the understanding we get from this is somehow incomplete without also understanding how the networks are generated in the first place. Okay, so what elements of the brain are underlying these networks, and how are these elements interacting to give rise to the observed networks? So that was missing from this particular kind of characterization. So that led me to apply for postdoctoral funding and also mobility funding, postdoctoral funding from HIIT, Helsinki Institute of Information Technology, and FCAI, Finnish Center for Artificial Intelligence, for a project to understand the structure function relationship underlying observed networks in MEG. So this was work in collaboration with Sami Kaski and Matthias Palva, and then the first part of the project was actually done in IMSC on a mobility grant from Research Council of Finland and Department of Science and Technology India, along with Sita Bro as collaborator. And we've particularly focused on networks of phase synchronization. So phase synchronization is one type of interaction seen in the brain, and the left panel just shows you strong brain regions at a given time lag, and phase synchronization is considered to be important because it is considered to regulate the communication between different brain regions. So just to give you a very brief illustration, so when the lag of the phase synchronization matches to the time taken for the action potential to travel between the brain regions, then phase sync is considered to facilitate communication between brain regions. But when the lag of phase sync is mismatched to the time taken for the activity to travel between brain regions, then phase sync is considered to hamper communication between the brain regions. So in that sense, phase sync is considered to regulate or gate communication between brain regions, and that's why it's considered to be important for cognitive function. And also specific networks of phase synchronization or distinct networks have been identified from MEG data, for example, or EEG data for specific cognitive tasks. So these networks of phase sync are likely to be functionally important, but we do not understand exactly how these phase sync networks are generated in the first place. So this is work that was published in Neuroimage, by the way, and why it is important from a clinical point of view is that, for example, in Alzheimer's disease, in MEG data, if we look at MEG data, so we see hypersynchronization or more than normal phase synchronization between certain brain regions. So we can see this, and this can be a sort of biomarker of Alzheimer's disease, and it has been proposed as a biomarker. But we do not know how the hypersynchronization is generated or what are the causes of this. So understanding the structure function relationship can also so greater than normal phase synchronization. So for example, if you compare phase sync between healthy controls and people with Alzheimer's, for example, so the Alzheimer's disease patients, individuals, they have greater than normal phase sync between certain brain regions at a certain frequency. So it's just greater than normal. So in that sense, it's stronger phase. Sorry. Yeah.
It would be related to the second case where you.
This one.
Sorry, the previous one. Schematic you showed the case where spike is missing peak excitability.
Yeah, yeah.
That's what you mean by hypo.
Not exactly. So I suppose what I mean is that, for example, this is strong phase sync. This is strong phase sync. So just imagine a case where the phases of oscillation are like not as well aligned in this. Okay, so then that would be like weaker phase sync. So when I talk about hypersync, it would be more like this compared to compared to if they were not so well aligned. Just stronger than normal alignment of phases, stronger phase alignment of phases compared to what is seen in the healthy controls. Hypersync. This is what I mean. Or I suppose why it is called hypersync is that, generally speaking, if you look at brain disorder, you would expect to find lower than normal phase sync, lower than normal interaction. But in Alzheimer's, it's sort of considered, or it is observed that it is higher than normal among certain brain regions, and it was considered to be a compensatory effect. But now it is considered that that is a marker of the actual pathophysiology. It is not compensatory, but it's actually reflecting what is wrong. So we don't understand the causes of hypersynchronization, although there have been some hypotheses about what causes this in some papers. For example, it might be that the amyloid beta deposition promotes neuronal hyperexcitation, which then impairs the excitation inhibition imbalance, which then impairs information processing neuronal circuits, which would then cause network dysfunction, which would then cause cognitive impairment. So this is sort of like relatively speculative, like hypothesis about how this hypersynchronization might be occurring, and then how that might cause cognitive impairment. But then if we had a good understanding of the structure function relationship, we could be much more precise in this. Okay. So then that's why it's important from a clinical point of view to also understand the structure function relationship. One example, and yeah, so like I said, improved understanding of the generation of hypersync would enable us to have more interpretable biomarkers of diseases like Alzheimer's disease, which would be potentially more sensitive and specific because they reflect the actual pathophysiology. And it would also constitute, if we had understanding of the impaired structure contributing to the impaired functional hypersynchronization, then that would also constitute targets for pharmaceutical interventions. So it's important to understand the structure function relationship essentially. So just before I get into the next part, which is the details of the project, are there any questions? One or I mean, there's probably time for one or two questions before I get into the details of the project.
So how much higher is it? So you said it's higher than normal. So epilepsy is also,
Yeah.
excessively high synchronization. So
Yeah.
like on a comparative scale, how would epilepsy and Alzheimer's disease relate? I mean,
Lower than epilepsy, and then epilepsy, from whatever I know, it's like zero lag phase sync, while this is like there is a lag, and it is lower phase sync compared to epilepsy, and it's also just in alpha and beta frequencies, and it's also not it's not across the whole brain, but just between a few anterior brain regions, if I'm not mistaken. So it's localized, but there is hypersync. But definitely, so epilepsy would be, I guess, at the continuum. If you're looking at the continuum, epilepsy would be at the far end of the continuum. Like it's sort of like global, and it's like very high. This is like more localized, and it's relatively lower.
so has other diseases also been linked to such hypersynchronization? Let's say Parkinson's or something.
Parkinson's, I don't know, but I do know that this hypersync is seen even at the early stages of for example, subjective cognitive decline, mild cognitive impairment, Alzheimer's. So this hypersync is seen at pretty early stages.
It's not there in late stages?
Also at late stages. In terms of Alzheimer's, like the different stages of Alzheimer's, it's seen at a pretty early stage, hypersync, and other disorders, so I don't know of instances of hypersynchronization.
In Parkinson's, there is some observations.
Yeah, Parkinson's has oscillations. So as you know, Parkinson's, so there's some beta band aberrant phase sync, which can also be corrected by this like deep brain stimulation and things like that. Yeah, so there is oscillations, there is phase sync, aberrant phase sync, but I don't know exactly like where, and also if it's hyper or hypo. I'm not sure about that. Yeah. Yes.
how much phase lag there is.
Yeah. How much alignment of phases at a given lag?
Okay, so when in normal cases,
Hmm.
there's a in the previous slide I saw a 90 degree,
Yes.
90 degrees. So there's generally a phase difference of 90 degree between
No. So yes. So here I'm just showing that this is this constitutes the point at which the waveform is at a phase of 90 degrees, pi by 2.
so the green and the two separate.
Yes.
Alright.
Yeah. Hypothetically, I'm just showing example of two hypothetical oscillations between two different brain regions phase sync at a given lag, stroke phase sync at a given lag.
Okay. And so you're saying in case of pathological conditions, the phase becomes smaller.
Yeah, so in case of Alzheimer's disease specifically, so the alignment becomes stronger compared to normal alignment, but the phase lag. So actually, people haven't studied this, like how the phase lag, phase synchronization lag is affected, but the alignment of phases becomes stronger. If Okay, so I suppose there are like two different aspects to this. One is the strength of the phase sync, and one is the lag of the phase sync. But what I'm talking about is the strength of the phase sync. What I'm talking about is the strength of the phase sync.
Yeah, if you'd like to explain that or something.
Yeah, sure. Yeah.
Like this.
Okay, so it's just okay. This is time, and then for example, amplitude in terms of millivolts, for example. So strong phase sync would be something like this is one oscillation, and then at a given lag you have another oscillation. Okay, so this is I guess strong phase sync, because even though it had a lag, there is a certain alignment of phases at a given lag. Okay, but for example, weak phase sync would be weak sync would be okay. So this would be one oscillation, and then like just imagine. Okay, so here there is no like well, in the sense like at least like so there's no like very obvious alignment of phases between this waveform and this waveform compared to here where there is more obvious alignment. But I'm not sure if so I'm not sure if this is also very disordered, but essentially like the alignment would so for example, here if you were to take the difference of instantaneous phases, and then just take out the time dimension and just plot a histogram of the difference of instantaneous phases, that would be concentrated. But in this case, it would be like around the unit circle in that sense. So that would be weak phase sync.
So one of the waveforms is probably very heterogeneous and noisy.
In this case, for example, in this case, or if both of them are like somewhat heterogeneous, then that would be weak phase sync. But here, essentially the histogram of the difference of instantaneous phases would be concentrated, even if yeah. So you use a measure called phase locking value, so which would give both the strength. So that would be okay. So E of T1 minus T2 1. Yeah. So it's basically yeah. So this is what it is, and this would be a complex number. And then the absolute value would be the strength, and then the angle would be the lag. So essentially this would be instantaneous phases, and then you take the instantaneous difference of instantaneous phases, and then if you were to
Two eyes here. One eye is I guess.
Okay, sorry. So okay, t is equal to 1 to.
So at different times you are looking at.
Yeah, different times. So across time, you would see the concentration. You would measure the concentration of the distribution of instantaneous phases.
So if you have two phases which are completely like anti-phase to me, for example,
Yeah.
they maintain the phase difference throughout, would
Yeah.
that correspond to strong phases?
For strong, yes, strong. So it would just so essentially you're just trying to assess how concentrated the histogram of circular histogram of instantaneous circular histogram of difference of instantaneous phases is, even if it's not concentrated at 0, it would be 180 or that kind of thing. Yeah, yeah, very concentrated, or like more than normal, But as Hitabro said, in epilepsy, epilepsy is where it's like very high. The sense like across the brain, so the phase sync is like so the phase sync between like brain regions is like very high, and also like close to zero lag phase sync in epilepsy. In Alzheimer's disease, it's not as high and also localized. It's higher than normal, higher than healthy controls. That's what I mean.
Also, this effect of lag is that we don't has not been studied. I mean,
Correct. Yeah, an effect of delays. So the lag is the functional. So we're talking about phase link. I suppose like we mentioned phase sync lag. We're talking about a functional construct, but then I'm talking about delays, which is more structural in terms of the anatomy. So that hasn't been studied, which is what I mentioned in my abstract. Is that what you're asking about, like what I had mentioned in my abstract, or what I mentioned in the talk just now?
what is it just now?
Okay, so like what hasn't been studied is the effect of the conduction delays on the observed networks of phase synchronization. So I will be coming to that, of course. Okay, so the lag, yeah, I understand what you mean. So the lag, so essentially when people compare the networks, they usually estimate as the absolute value of like this measure, which is the strength of the phase sync, or the degree of alignment of instantaneous phases, and they would like define a network according to that, and then compare that network between two experimental conditions. Okay, so that is what I meant when I said that the strength of phase is studied, but the lag of phase sync has not much been studied. Has not much been studied. Yeah. Okay, so yeah. Okay, so yeah. So there is some knowledge on. So there is some knowledge based on neurophysiological studies on how phase sync is generated, and that is represented in a simplified way in this particular schematic, where in the dashed box is a model of an individual brain region, just a single brain region, where UE and UI are excitatory and inhibitory neuronal populations. And according to the existing current knowledge on phase sync, so oscillatory activity which is required for phase sync, oscillatory activity is generated by the interaction between excitatory and inhibitory neuronal populations. So according to this push-pull dynamic, excitatory population and inhibitory population interact with each other to generate oscillatory activity, which is then transmitted along anatomical connections to other brain regions. So the oscillatory activity is transmitted, and then that sets up a phase sync relationship with a distant brain region, with another brain region. Okay, so this is the sort of like basic neurophysiological knowledge of how phase sync is generated, or in other words, local oscillations interact with anatomical connections to generate networks of phase synchronization. Okay, so this would be the sort of summary of the current understanding of how phase sync is generated, and that has also been formally expressed in terms of these differential equations, and which are represented by these brain computational models, which can be simulated to generate artificial networks of phase synchronization. Okay, so this is just basic knowledge of how phase sync is generated. So in this, just to explain a little bit about like what each of the symbols mean. So WEE is the connection strength within excitatory population, WEII is within an inhibitory population, then WEI and WIE is connection strength between excitatory and inhibitory population. So this is from inhibitory to excitatory, and this is from excitatory to inhibitory. Then psi E and psi I are the external noise input. Then these tau E and tau I are the time constants of the excitatory and inhibitory population, which also influence the frequency of the oscillations. So, tau E and tau I. Then B E and B I are the thresholds of the logistic function, which convert the input activity to these populations to the output firing rates. Okay. And then these variables just scale the structural connections. So K and I had scale the structural connections. Okay. So these are just the meaning of the different of the different variables in the equation, and that is what is expressed here. But what is unknown is that for each of these anatomical connections, we also have a conduction delay. The delay the delay of the activity to travel from a region to another region. So that is expressed in this Tij matrix from each region to each other region. So we also have this as part of the equation, but we do not understand the role of the interregional delays in generating the observed networks of phase synchronization. Yeah.
So these connections between the excited population and the excited population and the inhibited, there's no delay aspect here.
Okay. So there are delays. It's like very less. So we in our model we consider them as negligible, but it would be very less, like a few milliseconds, 2 milliseconds, 3 milliseconds, this kind of thing. So there would be delays.
So I mean, essentially what I'm asking is, so there's some connection between the excited and inhibited, and also there's some connection between this entire like module with the other.
Yes. Yes.
Like physically, what is like what kind of connections are these? Or like, why is there a delay in that?
Okay. Yeah, this is a good point. Okay, so like, okay, so I suppose delay is always a ratio between distance and velocity, conduction velocity. Now within a given neuronal population, the distances would be like much lower. So then the delays would also be correspondingly much lower. Okay, so the structural delays, physical delays would be much lower. So there are finite delays, it's true, and if you wanted to make the model more realistic, you would include delays. Whether that would make a difference to the observed dynamics has to be seen, but if you wanted to make it realistic, you would include at least small delays. That's true. We don't include delays because the distances are not that much, so the delays would also be much smaller. While here distances would be much larger between brain regions, so the delays would be finite in the order of like maybe 10 milliseconds, 8 milliseconds, or like even more than that sometimes. So then that becomes non-negligible. So then we include that. How do we know the parameters? Yeah, this is a good point. I get that address in the project. So some parameters you can get approximate values from electrophysiological studies, mainly from animal electrophysiology. For example, time constant for excitatory population, inhibitory population. So for those, there are good animal electrophysiological studies of time constant of excitatory neurons, inhibitory neurons, which you can then use to define at least ranges. And then for some, so essentially most of the you can get from animal electrophysiology, but then those are just parameter ranges, and you're also making the assumption that the animal electrophysiology would be like somehow reflecting the human brain physiology. So that would give us ranges in many cases. Now we use the simulation based inference methods to take those ranges and then make them narrower, or in the sense that we would use the data, MEG data, to try and get as much information about the values of the parameters and try and make the distributions narrower essentially. Which is I guess like part of the technical contribution of this in that sense. Any other questions? Okay. Yeah. Yeah. Time scales. Okay. Okay. Tau E and tau I would actually, okay, so like tau E and tau I would be quite different on the order of a few milliseconds, like for example 15 milliseconds, 18 milliseconds for example. And we also see when we look at the animal electrophysiology that usually the So the so the time constant of the yeah, so like so for example, we had a database of animal electrophysiological studies, and I think we inferred that mean of the time constants for around 18 something for inhibitory. So just a few milliseconds. Now that is the time constants. Now the time scale, the frequency of the activity would also be largely influenced by the strength of the coupling between these populations. If the coupling is strong, then the time scales would be actually very similar. So like even though the time constants are different, so the time scales would be, or the frequency would be very similar if the coupling is strong. Okay, so we want to know about the role of the delays in generating networks of phase synchronization, because we already have some knowledge of local oscillation, but we don't know about the role of interregional conduction delays. Now there are three biologically plausible hypotheses we can infer from the literature about how the delays might play a role. Okay, so for example, it might be that the local oscillations interact with anatomical connections via distance dependent delays. So as I mentioned, the delays are always the ratio between the distance and the conduction velocity. Now according to this hypothesis, if we assume that all the anatomical connections have constant conduction velocity, then the delays would be purely distance dependent. Okay, so this is like one hypothesis which is probably simplistic, but this is the assumption of the BCM. Because we do not have any, well, it's difficult to delays just based on the distance, okay, assuming constant conduction velocity, and there's partial support for this assumption from some recent interconnected human electrophysiological studies, partial support. But it could also be that the delays are isochronous, in the sense that the nearby brain regions have low conduction velocity, faraway brain regions have high conduction velocity, so that the conduction velocity would then yield highly similar conduction delays. Okay, so in the sense that the distance between brain regions would be I suppose one factor, and then when it's counteracted by distance dependent conduction velocity, that would imply highly similar conduction delays. So this is another hypothesis, and this would be functionally advantageous for specific cognitive functions which require fine temporal coordination, because it would be isochronous in nature. Yeah, so yeah, in this case, correct. So it's true, like that is also a simplification that we make, and most other people make. Actually, if you look, the distances should be the length of the white matter tracts, but that is difficult to measure. Like so there are measures or like diffusion tractography, which estimates the strength of structural connections, also returns some estimates of the length, but those are also prone to a lot of biases like seeding and termination biases of the algorithm. Okay, so then like we use the Euclidean distance, which is usually an underestimation, essentially as underestimation. Okay, and then yeah, so it would be advantageous fine temporal coordination. There's also some evidence for isochronous delays from animal electrophysiology, and there is also a plausible mechanism of because of empirically observed activity dependent myelination, which is known to occur, which would then dynamically regulate conduction velocity. And computational modeling has shown that under certain assumptions, this regulation of conduction velocity would over time lead to isochronous delays. Okay, so there's a potential mechanism for isochronous delays, but one issue with isochronous delays is that faraway brain regions which have very high conduction velocity, which would imply highly myelinated anatomical connections, very thick anatomical connections, which would be metabolically quite expensive. So then there also has been theoretical proposals that it's neither just isochronous or distance dependent, but it's a combination of these two, which would effectively balance the need for temporal coordination while also keeping the wiring costs to be manageable. Okay, so these are the three hypotheses, but now since we cannot measure, since we don't have the tools to measure the conduction delays, we do not know which of these hypotheses is true. Okay, so essentially this project was about using the brain computational models to see which of these different hypotheses is best supported by our experimental data. So that's what we did in this project. And if you ask a machine learning person, for example, like how we have these three hypotheses, how to go about choosing which is true, they would probably refer to something like a model architecture problem, where we are deciding the model architecture. And how we would usually go about that is to have each of these models fit each of these models to a training data set, like a certain data set, in our case an MEG data set, and then a validation data set to choose between the fitted models based on predictive performance. Okay, so you have a held out separate data set where we would choose between the fitted models based on the predictive performance. Okay, so this is how I suppose we would go about it conceptually, and this is what we also do. But the difficulty here is that fitting these high dimensional BCMs, so we have 12 to 14 parameters in these brain computational models. So fitting them is technically challenging because we cannot use the standard likelihood based methods to do the fitting. So the likelihood based methods, they use a likelihood function which relates the model parameters to the observed data. But those likelihood function is difficult to formulate for these brain computational models, or it is intractable. So using the likelihood based method to do the model fitting is not an option in most cases in the case of these BCMs. And people have used for these kind of cases, people have used simulation based inference approaches. Okay, and simulation based inference methods. Was there a question? Sorry. Okay, so simulation based inference methods take an empirical approach to the fitting, in the sense that they would simulate the BCM at a number of different combinations of parameter values, at several different combinations of parameter values, and then just choose those combinations of parameter values, generating model dynamics similar to the empirical data. Okay, so it's a rather empirical approach to the model fitting in that sense. But as you can imagine, so this approach requires fairly exhaustively sampling the parameter space. Okay, and then so then that is a problem, because of that limitation, you can fit around 5 BCM parameters. Even if you were to fit 3 BCM parameters, you would have to exhaustively sample this 3D parameter space, and for a moderately dense sampling you would have to do around 27,000 simulations, and each BCM simulation, at least in the BCM that we use, can take up to 120 hours, up to 5 days. So then that becomes computationally infeasible to use the standard SBI methods to do the model fitting for the 12 to 14 parameters that we want to fit. Now, sorry? Okay, so that is basically like 30 different samples of each axis, 30 into 30 into 30 into 30, 9, yeah, that's what. Well, in the sense, like basically, I suppose you have like this, you have this range of parameter values which are plausible for for a particular parameter, and then you want to densely sample the parameter space at a sufficiently dense sampling. So then I have just chosen like 30 levels per axis, but you can go to 100, for example, maybe at least 10, which would then mean 1,000 simulations, which is itself quite a lot considering the simulation times. So once the BCMs are fit to the data, then we can use standard methods to compare the BCM. So that is not so much of an issue, but fitting the high dimensional BCMs is a technical challenge that we had to overcome to compare the different BCMs. So in order to do this, so we use this method called Ball-Fee, or Bayesian optimization for likelihood free inference. And Ball-Fee works by using Gaussian processes to fit high dimensional BCMs with a reasonable number of simulations, using a two parameter inference task for which we know the ground truth values. Okay, so this is just the BCM that we have been using, and I am just trying to infer the values of these two parameters, WEA and WEI, using synthetic MEG data for which we know the ground truth values. So the ground truth values are red lines in this case. And if we were to take a basic SBI method, just a simple basic SBI method, then we would have MEG data in this case, which is synthetic in our case, and then from that we would estimate a matrix of phase synchronization. Then the plot prior distribution of the model parameters based on the current knowledge about that parameter value. Okay, so we would have so you would like sample from the distribution matrix. We would do this multiple times for different combinations of parameter values. So for each combination, we would estimate a BCM based matrix, and we would essentially we would estimate a discrepancy between these two matrices. So for example, in this 2-parameter inference task, if we are assuming like 100 levels per parameter, then we would have around 10,000 simulations. If we were to do this 10,000 times, then we could generate this 2D discrepancy surface of the discrepancy between these two matrices for every combination of parameter values. Discrepancy surface does have a minima at the combination of at the true combination of parameter values. So in this case, we would end up with the model parameters. So the posterior distribution of data. Okay, so this is, but the problem is that use ball fee, which essentially we would do the same thing, but then after a certain number of simulations, in this case I have used 625 simulations. After a certain number of simulations, we would use a Gaussian process to estimate or to learn the mapping between the combinations of parameter values and the output discrepancies. So we would learn a Gaussian process to sort of learn the mapping between the combinations of parameter values and the resulting discrepancies from just a few simulations, and then use the interpolation ability of Gaussian processes to generate an approximation of the discrepancy surface. Okay, approximation with a much fewer number of simulations compared to compared to the 10,000 simulations that we have done here. And since the approximation looks similar to the original discrepancy surface, we would end up with similarly accurate posterior distributions even with much fewer number of simulations. Or by the same token, for a given number of simulations, for a given computational budget of number of simulations, we can infer that many more number of parameters using ball fee compared to what we can do with a basic SBI approach. Okay, so this is yeah. Correct. Yeah. Many more. That's true. So I suppose like it all depends on the discrepancy surface and how we define the discrepancy. And like for example, here I have said idealized, because as you say, if you were to actually infer the posterior distribution, there would also be probably a bump here, for example, and a bump here. Okay, so then there are inaccuracies and there are uncertainties, which also makes it useful to use this Bayesian approach, where we can have this multimodal posterior distribution rather than a point estimate approach. So it is true that if we had higher dimensional parameter surface, we would have that much more uncertainty. But I suppose we are trying to do the best that we can using the data that we have and the discrepancy measures that we have. Okay, so but as you said, there would be some level of uncertainty, or there would be some level of like well, I suppose there would be some uncertainty and some level of inaccuracy, because the discrepancy surface is not completely discriminative in that sense. It's true.
So like just following up on that question, so
Yeah.
the Gaussian processes,
Yeah.
how well do you think represent the data and can capture maybe exactly?
Okay. Yeah. So okay. So because they are non-parametric, they can flexibly learn the input-output mapping without actually imposing a certain functional form. So I think that makes them quite powerful to use as the surrogate models. And what we have seen is that when we simulate a BCM, there is a stochastic element because of the starting points. Now, if we estimate the discrepancy surface, if we estimate the discrepancy surface after running multiple simulations at each point and averaging, then we get an accurate discrepancy surface that can be fairly accurately modeled using a Gaussian process. But then if we just do one simulation at each point and then use a Gaussian process, then actually the noise actually in some sense confuses the Gaussian process. So then it does not become a very good approximation of the discrepancies. So it all depends on how you train the Gaussian process. I guess it's like some level of like well, I guess like some level of implicit knowledge that you build reduce the noise in the discrepancies by running multiple simulations at each point. That's what I mean. Now, yeah, so just to give the framework before I go into the results. So this is the framework we use. Essentially, so we had these three BCMs, and they were identical in all respects except for the way that the delays were specified in each of these BCMs. We fit each of these BCMs to this MEG data via the matrices of phase synchronization using Ball-free model fitting, and then once we fit the BCMs, we simulate the times. We simulate the fitted BCMs multiple times, and we generate corresponding matrices of phase synchronization, and then for a given decided mean discrepancy, we compute the acceptance rates when comparing each of these matrices to this matrix from a held out acceptance rates, and then use the acceptance rates to assign model probabilities to each of the BCMs. So essentially, this is the model fitting part, and this is the model comparison part. This is the overall framework that we employ to compare the different BCMs to see which one is best supported by the empirical data.
Sorry, I didn't understand the sequence. So you first have a model with network before fitting.
Yeah.
So here it's just some arbitrary network.
Okay. So we use MEG data set to fit the model, and then we use another.
Before fitting some association with the data that you're recording. It's some arbitrary network.
Yeah. So like those based network distribution. So let me draw a random sample from the prior distribution, simulate the BCM based on like those combination of parameter values, and then generate the model of data, not looking at this data. That's true. And then
the next step in the sequence.
so after the fitting, we would have the posterior distributions. Then we would simulate from the we would simulate the BCMs from the posterior distributions, or sampling from the posterior distributions, which would be simulating the fitted BCMs in that sense.
But it's an iterative process. So then you use the posterior distribution to make a model.
Yeah.
Test that model.
On the exactly. So
No, but you have a sequence of things, which is what I'm trying to understand.
okay.
Do you start with a given network?
Yes.
Then, because every network will have the corresponding parameters.
Yeah.
And you kind of look for the posterior. Is that how you do, and how do you initialize the network? Like, what is the initial network that you?
The initial prior distributions. You mean prior distributions, or like?
Getting confused with the terminology, but I'm
Okay.
saying the network. This prior distribution, I understand
Hmm.
is the.
Yeah. So the network topology is given to you.
Okay. Yeah. So the structural network topology is given to us. Structural network.
Okay.
Yeah. Sorry, I should have mentioned that. So the structural network is given to us, and then and then of course the model functional form also. So the functional form is what.
The delays that you are fitting.
Yeah. So we're fitting all parameters of the model to compare the role of delays, because if
So that includes the delays as well as those weights.
yeah, weights, everything, like all these parameters. So all these parameters we are fitting for each of the model. Each of the models, including the delay specific parameters, and the structural topology, the topology of the structural network is given to us as. Yeah.
Now you have this three things.
Yeah.
Matrix which you show.
Yeah.
So is it like you're doing it iteratively? That is. Oh
No.
that's
No.
not
No.
what it is.
No. No. Sorry.
So then what is this isochronous delay, mixed delay, and distance dependent delay? Three different types of assumptions you can do.
Yeah, different types of assumptions. Different types of assumptions about the spatial distribution of the delays, which are biologically plausible assumptions about the spatial distribution of the conduction delays. So essentially, we are trying to compare these different hypotheses using the data. using the empirical data, and to do that we need to first fit the models, and then use the fitted models to do the comparison.
So you have essentially three matrices at the end of the day.
Yes.
One assuming isochronous, one assuming mixed, and one assuming distance dependent.
Yeah.
And then you compare it with the data to see which one is the best. Is that what you mean?
Yeah, yeah. So like three different matrices, or three different sets of matrices.
Right.
Sets of matrices. Yeah. Yeah. So we have three different a set of matrices. So here I have only shown one matrix, but essentially we would simulate multiple times, and then like I suppose from that set we would like, for a given mean discrepancy, we would compute the acceptance rates, in that sense, acceptance rate for each of these set of matrices, and then use that to assign model probabilities to each of the BCMs. Yeah.
So you're in those three cases,
Yeah.
asynchronous, mixed delays, and distance.
Yeah. Yeah. Yeah.
These three cases are actually you're allowing the key i's in the previous equation.
Yeah.
The previous slide, you're allowing, in case of synchronous delays, you're allowing all the DIs to be same.
Yeah. Isochronous. Isochronous. Yeah.
And in case of distance dependent, you're making them to be distance.
Correct. Correct. Yeah. So so essentially like so for this isochronous delays, so where there would be a mean delay and like little bit of. For this, it would just be the conduction velocity, because once you define the conduction velocity constant, then like everything else is specified in that sense for the distance dependent delays. And then for the mixed delays, basically you would have let me think. Yeah, you would have also a conduction velocity parameter. Then you would have a mean delay parameter, and then you would have a balance coefficient, in the sense like how weighted is the distance dependent and the isochronous delay. So this would be one parameter for the mixed delays. So you would essentially correct fitting. I understand. Now like when we talk about okay, so yeah, so it has more parameters, that is true. Okay, so it has more parameters, so in that sense like the fit could be better. Now okay, so like if you were to talk about it from a frequentist point of view, then we're doing the fit, and there is like room for like overfitting in that sense, because mixed delays has more parameters. Now when we have Bayesian inference, now there is some implicit guarding on the observed data to infer the posterior distributions, and sampling from that to do the fitting. Some room for like in some sense like getting a better fit with the mixed delays compared to the other models. Maybe I can discuss that with you after this, in the sense like it would essentially like it would essentially be guarded against because of the implicit regularization afforded by Bayesian inference, but we can discuss it in more detail after the talk. Okay, so I guess we're running out of time. Can I take around 10 more minutes or okay, so essentially so this is well, as you have already understood, one of the key points in using this algorithm is to define a good discrepancy measure. Okay, discrepancy measure to compare the BCM matrix and the MEG matrix. So here also I have illustrated how we chose the discrepancy measure for this 2-parameter inference example for which we already know the ground truth. So, if you look in the literature, people typically compare the matrices using a measure like root mean square error between the two matrices. But in the case of root mean square error, you are also prone to a number of other parameter combinations which also give low discrepancies, because root mean square error only compares the pointwise connection strength. It does not compare the pattern of the connections, for example. So, people have also used correlation or the 1 minus correlation as a discrepancy measure, but in the case of correlation, it compares the pattern of connection strengths, but it throws out information about the strength of the connections and the variability of connections. So, that was the reason for us using this measure called structural similarity index, which simultaneously compares the strength of connections, variability of connections, and also the pattern of connections. So, because we are simultaneously comparing all these different aspects of the matrix, we would be less prone to having parameter combinations which would also give lower discrepancies, despite them not reflecting the true combinations of parameter values. Okay, so as you pointed out, there is this region here which also has low discrepancy, but it is much smaller compared to, for example, this and this, for example. So, and the reason for that is because we are simultaneously comparing different aspects of the matrix, the strengths, the variability of connection strength, and the pattern, which would overall lead to more discriminative discrepancy surfaces and ultimately more accurate posterior distributions and more accurate inference of the parameter values compared to the other discrepancy measures. So we fit the BCMs as I mentioned, and these are the results of the fitting. So these are the different models: isochronous, mixed delays, and distance dependent delays. Between 12 to 14 parameters were actually fit for each of the BCMs. So the black outlines show the prior distribution of the model parameters, and the red outlines show the posterior distribution of the model parameters. And according to some convergence diagnostics that we used, we were able to fit all these parameters reliably. Okay, so we were quite confident that the fitting was performed sufficiently well to then do the model comparison after that. So when we did the model comparison, so this is a slide showing on the x-axis the that we defined to do the model comparison. The minimum discrepancy just says if the model matrices are close enough to the MEG matrix. Okay, so for a range of minimum discrepancies, we were estimating the model of minimum discrepancies. The distance dependent delays model is far more probable compared to the isochronous. Okay, so essentially the isochronous delay is least probable. Then as you start putting distance information into the delays, it becomes more probable, and then when it's purely distance dependent delays, it becomes the most probable. Okay, so it's a fairly clear answer to our question about which of these different models is best supported by the data. And also what we did not expect beforehand, we thought that distance dependent delays is somewhat simplistic, but the distance dependent delays is best supported by the data compared to the alternative methods, mixed delays and isochronous delays. So in terms of the contribution of this work, in terms of the neuroscience or the computational neuroscience contribution, it's just that we have now some information about the role of interregional delays in generating the network. So previously we had information about local dynamics and the anatomical connections, but now we have delays added to the story. So essentially these the insight is that local dynamics interact with anatomical connections via distance dependent conduction delays to generate interregional brain networks of phase synchronization. So this is the neuroscience or computational neuroscience contribution, but in order to achieve this, we also had to do the fitting of the high dimensional BCM. So that is the technical contribution. So in that also we were able to advance the state of the art, which is shown in this column on a number of different metrics. So the number of inferred parameters, we inferred between 12 and 14, while in our field it has only been up to like 5 parameters, and the discrepancy measure that we used also, as I demonstrated, would likely lead to more accurate posterior distributions. Then because we used a Bayesian inference framework, we were able to include prior knowledge, which would also lead to more accurate posterior distributions. The Gaussian process kernel which we used allowed for different scales of the discrepancy surface according to the different parameters. So parameter specific length scales, which was not the case which is not the case for the previous approaches. Then we also used many checks and diagnostics at every stage of the process, which I did not talk about, which made us more confident that we are on the right track in fitting and comparing the models. And then we used this embarrassingly parallel workflow to do the model simulations, which allowed us to do many simulations to fit the Gaussian process model, while the previous like all these steps or all these features of our fitting, we expect that they would allow us to fit the BCMs more accurately and infer the posterior distribution more accurately than what has been achieved before in the state of the art. So that's the technical contribution. But the more broader significance of the work is in the framework we used, because if you look at the literature in our field, cognitive neuroscience, the modeling and experimentation tends to mostly occur in parallel, and at the most maybe 2 or 3 parameters of the model are informed by the empirical data. But in our case, we use this SBI workflow, this model fitting and model comparison workflow, to actually inform the BCMs in a much more comprehensive way based on the MEG data. So we were able to use the SBI workflow to understand or to answer the question of how to specify the interregional conduction delay. So that interregional conduction delays, and so we achieved a closer integration between the modeling and experimentation than has been achieved previously before in our particular field, cognitive neuroscience. So just to close off the comments on this particular line of work. So the exciting thing is that we can use this same SBI workflow to make other modeling decisions about how to specify different aspects of the model to build increasingly well specified BCMs. So for example, if we wanted to make some decisions about how to specify the structural connection matrix, for example, or if we wanted to compare a simpler model with a more complex model, then we could use the same SBI workflow to do this model fitting, model comparison of different options, different modeling options. Or for example, if we wanted to model not just networks of phase synchronization, but also networks of amplitude correlation, for example, then we could just change the summary statistics of the model and then do the same or sort of follow the same workflow to have a BCM which encompasses not just networks of phase synchronization, but also other systems level phenomena. So essentially, the broader significance is that we were able to illustrate that the SBI workflow, illustrate with one example that we can use the SBI workflow to inform the model building with the empirical data. So this is essentially the idea is that we would be able to use this workflow to build increasingly well specified brain computational models of the brain activity in the future. So I think we are probably out of time, so I will just I'll just go to the summary slide because this would also take a lot of time. So I'll just touch on I'll touch on the planned future work in the summary slide, but I won't go into the future work right now. So as I mentioned previously, I've contributed methods to characterize healthy and disrupted functional network, but this was more from a neuroinformatics point of view, which led to some kind of incomplete understanding in that sense. So this led to a research program on understanding the structure function relationship of networks, where we use this SPI workflow to better understand the role of interregional delays. And essentially the envisaged future work at IMSC would be to build well specified BCMs using this SPI workflow, build increasingly well specified BCMs, so not just characterized networks of phasing, but also other types of networks, level phenomena like traveling waves, etc., using the same framework that we used in this particular paper. And in the long term, this would of course yield a deep understanding of the structure function relationship, which would help us understand how cognitive functions are performed, the neurophysiology of cognitive functions, and what goes wrong in brain disorders, the pathophysiology of brain disorders. So this would add a neuroinformatics element to the current work of the CompBio group and IMSC. And it would contribute both to the theoretical aspect like computational neuroscience, active matter systems, dynamical systems, biological network modeling, but also to the practical recent directions on machine learning for health and disease. So, it would encompass both these, and it would also contribute to the activities of IMSC Center for Disease Modeling. So, just to finish off, thank you to my collaborators, especially Professor Matthias Palva, Samuel Karski, Rick Henson, of course Sita Bro and Arijit. Then thank you to funding organizations, especially HIIT, FCAI, Human Brain Project, Research Council of Finland, DST, organizations including IMSC, Cambridge, Aalto, Reading, Helsinki, and of course last but not the least my family. Thank you.
So we have plenty of questions during the talk, but maybe one or two quick questions.
So can you say that all the tracks
Yeah.
equally myelinated?
No. So the myelination would basically influence the conduction velocity. So there's this linear relationship between the diameter of the track and the conduction velocity. So then, like when we are assuming spatially varying conduction delays, then we are actually assuming that the tracks are like differently myelinated.
So in this case, you found distance.
Correct. Yeah. So in that, yeah, you can say that sort of implies constant conduction velocity. Okay, so like of the models that like we looked at, this is the best approximation of the delays. Okay, so like in that sense, like probably the other models that we use to specify informative enough to exceed the distance dependent delays model, but there may be some other model which would account for the spatially varying conduction velocity, which would then exceed the distance dependent model, because in the sense that we know that the tracks assumption based on these models, we can assume that the conduction velocity is constant, so that the delays are purely dependent on distance, until another better model comes along which allows us to specify how the conduction velocity might be spatially varying, which would hopefully then exceed the distance dependent delays model. Does that make sense what I'm saying? So that of the models that we studied, the distance dependent model or constant conduction velocity is the best approximation, which as you say implies equal myelination. This is true. Now it's also related to the question you previously asked. So this might also be a confound to the results we found, because that essentially assumes the distance would be higher than that. So that would be underestimation of the distance, which would possibly confound the model comparison results that we found. So this is one possible confound, the assumption of Euclidean distance for the model comparison results we found, if it makes sense.
Does this have any into your like the motivation of Alzheimer's disease?
Yeah.
So, what's the
Yeah. Sorry.
do you have any thoughts about
Okay, I understand.
based on this finding?
Okay, Alzheimer's. Okay, so hypersynchronization. Now,
So I was thinking that since it's distance
yeah,
dependent,
yeah.
so does in the case of Alzheimer's there's like excitation from all over the brain happening? Because if there was excitation from a single point,
Yeah,
then because of distance dependence,
Yeah.
there will be lag.
yeah,
Right? That's what we see in general.
yeah,
At least
yeah,
in early brain. But in case of Alzheimer's, we're seeing hypersynchronization, so everyone's moving around.
yeah, yeah, yeah. So probably the okay. So I don't have any like direct comments, but the best way to do this would be to now take an immediate data set of Alzheimer's disease patients and then do the same model fitting, and then look at the parameter values. So I suppose like if so we would definitely get different parameter values. So then that would give us some mechanistic insight about like what structural neurophysiologically important parameters are different between these two cohorts. This is how we would do it. So then that would give us some like mechanistic understanding about the causes of hypersync, which is essentially like I guess like one aspect of the applied component of my future proposed work. So like building these models and then applying them in collaboration with clinical neuroscientists to understand the causes of, for example, Alzheimer's disease from a cause of Alzheimer's disease from a deeper neurophysiological perspective.
Okay, so
Yeah.
Yeah. So if you have further questions, you can catch him during coffee or during lunch and so on. So
Yeah,
let's
definitely.
thank Nitin once more for a wonderful talk.
Thank you.